Welcome to the deep dive. Today, we are tackling something huge, maybe one of the most fundamental puzzles in physics. What exactly is light?
Yeah, it's a big one. We're
hmm
basically going on a mission here, pulling together centuries of thinking, looking at the core texts from optics, from quantum mechanics.
All to try and pin down this slippery concept. What is light? It sounds simple, but it's not.
It's really not. And it goes beyond just physics, doesn't it? It
Yep.
touches on philosophy, how we understand reality itself. I mean, the tools we use to look at light sort of force us into seeing it in contradictory ways.
Like Heisenberg said, right? These mental pictures we get from experiments.
Exactly. The particle picture, the wave picture. It said they're both incomplete. Just analogies, really, that work only in certain situations.
We just have to kind of live with both views.
And that split goes way back. You had giants of science lining up on opposite sides for centuries.
Like Newton, Sir Isaac Newton back in the 17th century, he was firmly in the camp that light was made of, well, tiny particles. Corpuscles, he called them.
Right, like little bullets. But at the same time, you had people like Huygens and Hooke, too, arguing, no, light has to be a wave.
And for a long time, the wave folks seemed to have the upper hand. Thomas Young's experiment, the double slit one, early 1800s.
Oh, yeah, that was huge. It showed interference patterns clear as day. And that's something only waves really do. It looked like strong evidence.
It felt like maybe the argument was settled then, and then Maxwell came along and seemed to just cement it. Light is a wave. Case closed.
Well, that's what it looked like for a while.
That was-
Yeah, I mean, if you look back at the 19th century, the wave model wasn't just winning, it felt complete. Maxwell's equations, they were revolutionary. They provided this solid mathematical proof that light is fundamentally a wave.
A transverse electromagnetic wave, specifically.
Exactly. And those equations, they're just beautiful, aren't they? They don't just describe light, they cover radio waves, microwaves, X-rays, the whole electromagnetic spectrum.
Yeah.
All propagating fields.
It's amazing how they show the electric and magnetic fields kind of leapfrogging each other through space at this fixed speed.
The speed of light, yeah. But the really crucial thing for, practical stuff, for why the wave picture is still so vital for optical engineering today.
Why can't engineers just always think particles?
It's because almost everything in complex optics hinges on one key idea that comes straight from Maxwell's math, the principle of superposition.
Ah, right, because the equations are linear.
Exactly. So if you have two waves, wave A and wave B, and they both work as solutions to the waves equation, then just adding them together, A plus B, also gives you a valid wave solution.
So when waves meet, they just add up or subtract, depending on how they align.
Precisely. Their energy fields combine. That's the basis for interference, those bright and dark fringes in Young's experiment. It's all superposition.
And that applies to more than just simple slits, right? Like
Right.
modern cameras.
Oh, much more. Think about something like holography. A hologram fundamentally captures the interference pattern between a reference light beam and the light bouncing off an object. It's recording the phase information, how the waves add and subtract. That's pure superposition.
Okay, I see.
Or think about phased array systems and high-power lasers. They use multiple smaller beams, carefully control their relative phase again, superposition, to combine them into one incredibly intense beam.
So the wave math isn't just theory, it's the blueprint for a lot of high-tech gear. You mentioned polarization earlier, too. That's strictly a wave thing, isn't it? How does superposition explain why some light beams just won't interfere?
Yeah, that's a neat consequence. It boils down to geometry. For waves to interfere constructively or destructively, their oscillations need to be along the same direction, more or less.
Okay.
But if you take two light beams where the electric fields are oscillating at right angles to each other, what we call crossed polarization, they physically can't combine their energy fields in that additive or subtractive way.
And just pass through each other.
Essentially, yes. Mathematically, the dot product of their electric field vectors is zero. No interaction, no interference.
Which is why my polarized sunglasses work. They block waves vibrating the wrong way.
Okay, so the wave picture had math, elegance, experiments, engineering. It looked totally solid. It really did. It seemed like physics had the electromagnetic world all figured out.
Yeah.
Smooth sailing. Until people started looking really closely at hot objects and very high frequencies. Yeah.
Right, so the wave picture was looking perfect
Okay.
until, as you said, it started causing problems. What was the crisis? What made this beautiful classical picture start to crumble?
It all centered on black body radiation.
Yeah.
Now, black body isn't necessarily black. It's just a theoretical ideal object that absorbs any radiation that hits it, and then it emits light based purely on its temperature. like a hot piece of metal glowing.
Okay, simple enough. So scientists tried to use the wave theory, classical physics, to predict the spectrum of light coming off these hot objects.
They did, and that's where they ran into the ultraviolet catastrophe.
Ah,
A total disaster.
catastrophe sounds bad.
Right.
Where did the math go wrong?
It went horribly wrong at the high-frequency end of the spectrum, short wavelengths, like ultraviolet light, X-rays. The classical theory, the Rayleigh-Jeans law, assumed energy was continuous, like you could have any amount of energy.
Okay.
And it assumed that every possible way a wave could vibrate inside this hot object, no matter how high the frequency, could hold some energy.
And since there are, theoretically, infinite possible frequencies or wavelengths,
The theory predicted that a hot object should radiate an infinite amount of energy, and most of that energy should be blasting out in the high-frequency UV and X-ray range.
infinite energy, that's not what happened.
Not even close. If that were true, just turning on your kitchen toaster would basically vaporize you instantly with high-energy radiation. It was completely absurd, mathematically and experimentally. A huge failure for classical wave theory.
Okay, that's a serious breakdown. You can't just ignore infinity. So who fixed it and how?
The fix came from Max Planck, around 1900, and it was radical. To get a mathematical formula that actually matched the observed blackbody spectrum, he had to make a wild assumption.
Which was?
Quantization. He proposed that energy wasn't continuous after all. It could only be emitted or absorbed in discrete little packets or chunks. Like energy came in coins, not flowing water.
Wait, he didn't derive that from first principles? He just sort of forced the math to fit the data.
That's pretty much it. And that's why it was so revolutionary. He found an equation that worked perfectly, but only if he introduced a specific constant, which we now call H. Planck's constant. This constant linked the energy of a packet, epsilon, to its frequency. What the rule was, energy could only come in units of epsilon HFE wide, where n is just a whole number.
And he found the value for H just by curve fitting.
Essentially, yes. He treated H, which is incredibly small, about 6.626 times 1030 seconds, purely as a fitting parameter to make his formula match the experiments. He suspected it was just a mathematical trick at first.
But it turned out to be fundamental.
Absolutely fundamental. Planck's constant popped up everywhere in the quantum revolution that followed. By making energy discrete, Planck solved the ultraviolet catastrophe because those high-frequency vibrations could only get excited if they received a big enough energy packet, HF. There just wasn't enough thermal energy available to excite many of them, limiting the high-frequency output.
And those discrete energy packets, those became the photon, right? The particle of light.
Exactly. The energy of a single photon is given by EP way is HFW.
So what does that mean for, like, the light we see? Visible light. How much energy are we talking per photon?
It puts things in perspective. Photon energies are tiny on our everyday scale. For visible light, say from red to violet, you're looking at individual photon energies of roughly 1 to 3 electron volts.
So blue light photons have a bit more energy than red light photons?
Yet because blue light has a higher frequency. The quantum picture forces us to think about counting these individual energy packets. It brought the particle idea back with a vengeance. And to really get a feel for this duality, you just have to look at the different ways we actually measure and use light. We have technologies built firmly on the wave idea and others that absolutely depend on the particle idea.
Right. So the classic wave evidence is still Young's double slit experiment. You mentioned that. Shine light through 2 narrow slits.
And you don't just get 2 bright lines on the screen behind them.
No, you get that pattern of multiple bright and dark stripes, interference fringes.
Exactly. Those fringes, the bright spots, maxima, and dark spots, minima, in the light intensity, or irradiance, they're caused entirely by the paths the waves take from the 2 slits. Sometimes they arrive in sync and add up, sometimes they arrive out of sync and cancel out.
A purely wave phenomenon based on path difference and phase difference.
Correct. Try explaining that easily. If light is just particles flying straight, you really can't. Interference is the smoking gun for wave behavior.
Okay, wave box ticked. But then you said we also build detectors that treat light like, well, like little countable things. How does the tech show the particle side?
It comes down to how we detect very faint light. We use incredibly sensitive devices, like photomultiplier tubes or PMTs.
Okay.
These things aren't measuring a smooth, continuous flow of energy. They're designed to register the arrival of single photons.
One by one.
One by one. A single photon hits a spectral surface inside the tube, knocks out an electron. Then that electron is accelerated, hits another surface, knocks out more electrons.
An avalanche effect.
Exactly, a cascade or avalanche.
Yeah.
It amplifies that initial single event millions of times until you get a measurable electrical pulse. So you're literally counting photon hits. Click, click, click.
So if detection is fundamentally about counting these discrete hits, does that introduce any limitations, any inherent noise?
Yes, absolutely.
Okay.
It leads directly to something called shot noise.
Shot noise, like shotgun pellets hitting a target.
That's precisely the analogy. It's not noise from bad wiring or heat. It's the fundamental statistical uncertainty that comes from the fact that you're detecting a stream of randomly arriving discrete packets, the photons.
So if the light is bright, there are tons of photons arriving all the time, and the randomness kind of averages out.
Right. For bright light, the photon flux is so high that the statistical fluctuations are tiny compared to the signal, but when the light gets very faint.
The random arrival of those few photons becomes really noticeable, like a very sparse, irregular rain on a tin roof.
Exactly. That's shot noise. It sets a fundamental limit on how clearly you can measure a very weak signal. Crucial for things like astronomy or single-molecule imaging, where you might be counting just a handful of photons.
Okay, let's make that concrete. You had an example comparing different kinds of light beams with the same power, like infrared versus gamma rays.
Yeah, it's a great illustration. Let's say you have two beams both delivering exactly 1 milliwatt of power. Pretty low power. Now, if that's an infrared beam, the photons have relatively low energy, long wavelength. To get 1 milliwatt of power, you need a huge number of them. Something like 50 quadrillion photons hitting per second. 5 times 10 to the 16.
Bro, that's a torrent, so shot noise is probably negligible there.
Pretty much. The flow is so dense it seems continuous. But now take that same 1 milliwatt of power, but make it a gamma ray beam.
Gamma ray photons have way more energy, right? Very short wavelength.
Massively more energy per photon. So to get that same 1 milliwatt of power, you need far, far fewer photons. Only about 500 billion per second. 5 times 10 to the 11.
Still a lot, but way less than the infrared beam.
Orders of magnitude less. And because there are fewer, more energetic bullets arriving randomly, the statistical fluctuations, the shot noise, become much more significant relative to the total signal.
So the more energy each individual photon carries, the shorter the wavelength, the more particle-like and noisy the beam appears, especially at low power.
That's it exactly. You simply cannot ignore the particle nature when detecting light, particularly high-energy light.
Okay, so we've got waves causing interference, we've got particles causing clicks in detectors and shot noise. It's definitely both. For decades, physicists kind of just used whichever model fit the experiment they were doing right. A bit unsatisfying.
Yeah, it was like having two different toolkits. You use the wave toolkit for designing lenses and the particle toolkit for understanding detectors. But how do they actually connect? How does reality unify them?
So what was the breakthrough, the grand synthesis?
That came really in the mid-20th century with the full development of quantum electrodynamics, usually just called QED.
Ah, Feynman, Schwinger, Tominaga, Nobel Prize stuff.
The very same. QED is essentially the mature, incredibly precise quantum theory of how light and matter interact. And it finally resolved this wave-particle business.
And how does it do it? What's the core idea that bridges the gap?
Well, one really powerful way to think about it comes from Richard Feynman's approach, the idea of a sum over paths, or path integral.
Sum over paths. Sounds intriguing.
It is. Instead of thinking of a photon traveling along a single specific path from A to B, like a tiny billiard ball,
Yeah.
QED, says the photon, in a way, explores all possible paths it could take to get from A to B simultaneously.
Wait, all paths, even ridiculously covey ones, how does that even work?
It's not that the particle physically splits up and goes everywhere. It's more like, well, the math involves calculating a contribution, a complex number representing amplitude and phase for every conceivable path. Then you add all those contributions up.
You sum up the results from all possible histories.
Kind of, yeah. And because you're adding complex numbers with phases, they interfere with each other. Paths that are similar tend to add up constructively, while wildly different paths tend to cancel each other out through destructive interference.
Ah, so the wave-like interference is built right into this summation process.
Exactly. It emerges naturally from summing over all possibilities.
Okay, so QED does this incredibly complex sum over all paths. What's the final result? How does it connect back to what we actually measure, like light intensity?
And this is the really elegant part. When QED calculates the total probability of detecting a photon at a specific point B, after summing up all those path contributions, that final probability value,
Yes.
it turns out to be exactly proportional to the irradiance, or intensity, that you would calculate using Maxwell's classical electromagnetic wave theory.
Whoa! Okay, hold on. So the thing we thought was a physical wave, Maxwell's wave, is actually a map of probability.
That's the modern understanding, yes. The classical electromagnetic wave, its intensity pattern, isn't a physical substance waving. It's the probability density field for finding a photon.
So the wave picture is what emerges when you have tons and tons of photons, and their individual probabilities just smooth out into this continuous-looking pattern.
Precisely. It's a statistical approximation that works incredibly well when you have high flux, lots of photons. But fundamentally, the probabilities are governing the behavior of individual particles, the photons.
So the wave describes the probability of finding the particle. That's the synthesis.
That's the core of it. QED provides the underlying framework where the particle nature, discrete detection events, and the wave nature, probability distributions, interference,
Yeah.
are just two facets of the same quantum reality.
From Newton's particles to Maxwell's waves, and finally, probability waves governing particles. That's quite a journey.
It really is, and it works beautifully. It allows us to seamlessly connect the design of, say, a radio antenna, very classical wave, to the operation of a quantum sensor detecting single photons. Both descriptions are valid, and QED tells us how they relate.
So we've traced this amazing story from classical waves ruling the day with Maxwell and superposition, through the crisis of the UV catastrophe forcing Planck to invent the particle, the photon, seeing the evidence for both interference and shot noise, and finally landing on QED's synthesis where the wave is really about probability.
Yeah, the classical wave pattern is essentially the probability map for where you're likely to find the particle, the photon.
It's a beautiful resolution. But to leave you, our listener, with something really mind-bending to think about, consider this. The source materials mention experiments, like the Mach-Zehnder interferometer, where if you send photons through one at a time, a single photon seems to somehow explore both possible paths inside the device. Until you try to peek and see which path it took, then it snaps into behaving like a particle on just one path.
The act of measurement changes the outcome. Classic quantum weirdness.
Right. Now, connect that to Feynman's sum over paths in QED, the idea that the photon explores all possibilities. And then consider that the classical laws of physics, like Newton's laws or Fermat's principle of least time for light rays, which seems so deterministic, well, they can actually be derived from QED. They turn out to be just the path of highest probability that emerges when you sum over all those quantum possibilities.
The classical world is the most probable quantum path, essentially.
So here's the thought. If the fundamental way light, and maybe everything, behaves, is by exploring all possibilities simultaneously, as described by QED, and our everyday classical reality is just the most likely outcome of that infinite sum, what does that truly imply about the nature of reality itself? Is every movement, every interaction around us just the universe calculating probabilities across countless potential pathways, and we only perceive the winner?
Are all possibilities somehow real until one becomes manifest?
Something deep to ponder next time you're simply enjoying the sunlight.